Now let's discuss short circuit test. From open circuit test, the shunt branch elements of approximate equivalent circuit of transformer are found, that is R0 and X0 are found from open circuit test, as well as the transformer iron losses are found from open circuit test. And from the short circuit test, the series branch elements of the approximate electrical equivalent circuit of transformer are found, that is R01 and X01 or R02 and X02, depending on the side at which the meters are placed. And also from short circuit test, transformer copper losses are found. Therefore, short circuit test is used to find out the series branch elements of the transformer and the transformer copper loss. Open circuit test is preferred on LV side with HV open, whereas short circuit test is preferred on HV side with LV side short circuit. Therefore, first let's discuss how to perform this short circuit test and how to find these R01 and X01 or R02 and X02, and also let's find out what happens if the short circuit test is performed on other than the preferred side of the transformer. And let's also discuss why UPF wattmeter is to be used in short circuit test to measure the input power. Short circuit test is preferred to perform on HV side of the transformer with LV side short circuited. LV side of the transformer is short circuited with a thick wire or ammeter. To measure the input power, here UPF type of wattmeter is used, and to measure the input current, MI type ammeter, and to measure the input voltage, MI type voltmeter. And these meters are connected like this, and the supply is given through a single phase variac. Procedure: the first step is connect the circuit as shown in figure, and the second step is by varying variac apply rated current, and then the third step is note down meter readings and find out R01, X01 or R02, X02 and copper loss of the transformer. So connect the circuit as shown in figure, and we must short circuit the LV side of transformer with a thick wire, or we can short circuit with an ammeter. And then by varying variac we must apply rated current here, whereas in open circuit test by varying variac we are applying rated voltage. Here we must apply rated current. So rated current is found out by rating of the transformer divided by the HV side voltage. So vary the variac till the ammeter reads rated current, and this current is represented with ISC, and voltmeter reading is represented with VSC, and wattmeter reading is represented with WSC. And here you must make a important note that the rated current is obtained at 4 to 5% of rated voltage. That is, if suppose the HV side voltage is 100 volts, then the rated current is obtained at 5 volts. That is, very low voltage applied to the HV side. Wattmeter reading is represented with WSC, which can be equated to ISC whole square into R01. That implies R01 is equal to wattmeter reading by square of the ammeter reading. and the ratio of voltmeter reading VSC by ammeter reading ISC gives you the impedance Z01. As here Z01 and R01 are known, we can find the X01, which is equal to root over Z01 square minus R01 square. Now let's see how to find the copper loss of the transformer. It is known that total input power is equal to total output power plus losses, and in transformer losses are classified into major losses plus minor losses, and as minor losses are very low, these can be neglected, and the major losses are copper losses and iron losses. From the losses topic, it is discussed that copper loss depends on the current and iron losses depends on the voltage. In short circuit test, as very low voltage is applied, that is 4 to 5% of the rated voltage is applied at the input, so the iron losses are very low, and because of which we can neglect these iron losses. And here in this short circuit test, the output terminals are short circuited through an thick wire, which means the terminal voltage V2 is 0. So terminal voltage V2 0 means the output power V2 I2 cos phi 2 is 0. So this is 0, which implies the total input power is equal to copper loss of the transformer. And here in short circuit test, we are making use of UPF type of wattmeter to measure the input power. So from this relation, as input power is equal to copper losses, which means that the wattmeter reading will indicate the copper loss of the transformer. This is how the series branch elements R01 and X01 and copper loss of the transformer are found from short circuit test. Now let's discuss what happens if SC test is performed on other than the preferred side. This is the preferred side of the transformer at which the short circuit test is to be performed. And now we are discussing what happens if the short circuit test is performed on other than the preferred side. That is, if the test is performed on LV side with HV side short circuit. To understand that, let's consider an example. Let's take the transformer with 3300 volts by 220 volts and 33 kVA rating. For that, let's consider two cases. That is, if test on preferred side and if test on other than preferred side. That is, here on HV with LV short circuit, and here that is on LV with HV short circuit. Here in this case on HV, the rated voltage is 3300 volts and rating of transformer is 33 kVA. That implies the rated current to be applied is 33 kVA by 3300, that is equal to 10 amperes. And come to this case, here the rated current to be applied is 33 kVA by rated voltage. So as here test is performed on LV side, so LV side voltage is 220 volts, so 220 volts, that is equal to 150 amperes. And it is discussed that in short circuit test, rated current is to be applied, and that rated current is obtained at 4 to 5% of rated voltage. And in this case, as the test is performed on HV side, so the rated voltage is 3300 volts, and this 10 amperes is obtained at 4 to 5% of 3300 volts. So VSC is equal to 5% of 3300 volts, which is equal to 165 volts. And come to this case, here the rated current is 150 amperes and this rated current is obtained at 4 to 5% of the rated voltage. And here as the test is performed on LV side, So the rated LV side voltage is 220 volts. So Vs is equal to 5% of 220 volts, which is equal to 11 volts. Now compare these two. If the test is performed on preferred side, the rated current to be applied is 10 amperes. Whereas if the test is performed on other than preferred side, the rated current to be applied is 150 amperes, which is not readily available. And similarly, if you compare these two voltages, the accuracy of reading this voltage value is very high when compared with the accuracy of reading this voltage. As the accuracy in this case is good, so the results obtained are accurate. Whereas in this case, as the accuracy is not good, the results will not be accurate. So here are the problems that we face if the test is performed on other than preferred side. That is, large current source is not readily available and high range meters are required and results are not accurate. So because of these reasons, short circuit test is not preferred to perform on LV side with HV side short circuit, and short circuit test is to be performed on HV side with LV side short circuit. And now let's discuss why UPF wattmeter is used to measure input power in short circuit test. To understand that, let's recall the concept of ideal transformer. In case of no load ideal transformer, input power is equal to output power is equal to 0. That is, in case of no load ideal transformer, the power intake by the transformer is 0. Whereas in case of actual transformer, transformer will drive some power, and that power is used to meet the core losses in the transformer. And whereas in case of loaded ideal transformer, transformer will drag input power at load power factor. And in case of actual loaded transformer, transformer will drag the input power close to load power factor. And let's also discuss a simple concept on load. That is, if load on the transformer is connected, because of this load there will be a current in secondary. And now if load is increased, that is, here load is connected in parallel to the existing load, and let us suppose this load be resistive load of value 5 ohms, and let this load be resistive value of 5 ohms. And when load is increased, that is, when extra load is added in parallel with the existing load, observe that as these two are connected in parallel, the effective resistance value is 5 into 5 by 5 plus 5, which is equal to 2.5 ohms. This implies that by increasing the load, the effective value of the impedance will get decreased. If effective value of impedance gets decreased, the current value will get increased. So if you go on increasing the load, that is, if you go on connecting the loads in parallel, then the effective value of the impedance will get decreased more and more. And if it gets decreased more and more, the current will increase more and more. And this will help you to understand why to use UPF wattmeter. And that you can understand from the Phasor diagram. So if suppose this is the flux and this be the input voltage V1 of transformer, and let this be the induced voltages E2 and E1, and it is known that this will be the no load current I0. When there is no load connected to the transformer, then the primary current of transformer is I0. But when load is connected, extra current I2 dash will flow in the primary winding. So the primary current now is I1, which is equal to vector sum of I0 and I2 dash. But I2 dash is decided by current I2. Let the load be resistive load. Then if this is V2, then I2 will be in phase with V2. And for k is equal to 1, I2 is equal to I2 dash. So I2 will be in exactly opposite to I2 dash, and the vector sum of I0 and I2 dash gives you primary current I1. So the resultant of I2 dash and I0 is I1. If there is no load on transformer, then the primary power factor is phi naught, which is the angle between V1 and I0. But when load is connected, the primary power factor angle is phi 1. So which is the angle between V1 and I1. By comparing phi naught and phi 1, phi naught will be greater than phi 1. That implies no load power factor will be less than loaded power factor, and at full load condition the effective impedance value is very low, which implies the current is very high. That is, let's consider full load. So at full load the maximum current flows in the transformer, and this short circuit can be considered as the full load condition, because by short circuiting maximum current will flow in the transformer secondary. That is, IT will be very high, which implies I2 dash will be very high. If this is high, now the resultant of I2 dash and I0 will be I1, which will move like this, and now the angle between V1 and I1 is further reduced, and if it is further reduced, that is phi 1 will be around 20 to 30 degrees. That implies cos phi 1 will be greater than or equal to 0.6, and which can be considered as high power factor. And from this you can note that by short circuiting the secondary terminals of transformer, full load condition is obtained, because of which there is a maximum current flowing in the transformer, and because of which the primary power factor angle is 20 to 30 degrees, and which implies that power factor will be greater than or equal to 0.6, and which is considered as high power factor. So this primary circuit is high power factor circuit. And to measure the power with good accuracy, we are making use of UPF type of wattmeter in short circuit test. From this circuit you can note that the current is equal to the ratio of voltage to the impedance. So here ISC rated is equal to short circuit voltage by the impedance of the transformer Z01, and ISC steady, that is steady short circuit current, is given by the ratio of rated HV voltage by the impedance Z01. And if you compare this, as short circuit voltage is very low, so ISC steady current is greater than ISC rated current, and the ratio of ISC steady by ISC rated is equal to ISC steady is E1 by Z01, and ISC rated is the short circuit current ISC, which can be taken as I1. That implies ISC steady by ISC rated is equal to 1 by, and here I am taking E1 to the denominator, so I1 Z01 by E1, and this represents the per unit impedance drop. So 1 by per unit impedance drop, and per unit impedance drop can be simply termed as per unit impedance. So ISC steady by ISC rated is I1 is equal to 1 by per unit impedance, and which can be taken as equal to 100 by percentage Z, and that implies ISC steady is equal to I1 into 100 by percentage Z. This is the important relation which is considered in designing of transformer. And now finally, this numerical example will clear the most common doubt on OC test and short circuit test. In this numerical example, it is asked to find the electrical equivalent circuit of transformer by using the open circuit test data and short circuit test data. This is the schematic diagram of transformer. by bringing the secondary side parameters to the primary side, or by bringing primary side parameters to the secondary side, we can obtain the electrical equivalent circuit of transformer. And this is the approximate equivalent circuit of transformer, and this equivalent circuit of transformer is obtained by transferring the secondary side parameters to the primary side. So is why R01 is equal to R1 plus R2 dash, where R2 dash is the transferred secondary resistance, and similarly X01 is equal to the XL1 plus XL2 dash, where XL2 dash is the transferred secondary leakage reactance. So R2 dash is equal to R2 by K square, and XL2 dash is equal to XL2 by K square. And if you transfer primary parameters to the secondary side, then we get the equivalent resistance R02 and equivalent reactance XL02. And it is discussed that from open circuit test we can find the shunt branch elements R0 and X0 of electrical equivalent circuit of transformer, and we can also find the iron loss of the transformer from open circuit test. And from short circuit test we can find the series branch elements of the electrical equivalent circuit of transformer, and we can also find the copper loss of the transformer, and that series branch elements could be R01 and X01 or R02 and X02, depending on the side at which the meters are placed while performing the short circuit test. From this question you can note that OC test is performed on LV side and short circuit test is performed on HV side, which are the preferred sides of the transformer. From open circuit test data we can find the shunt branch elements R0 and X0, and from short circuit test data we must first decide whether we are getting R01 and X01 or R02 and X02. And observe here that short circuit test is performed on HV side, and here HV side is secondary side of the transformer. So from this data we are getting R02 and X02. But to get the equivalent circuit of transformer we need to find R01 and X01. So from R02 we must find R01, and from X02 we must find X01, where K is the transformation ratio constant, which is equal to N2 by N1, which is equal to E2 by E1, where E2 is the secondary induced voltage and E1 is the primary induced voltage. So now by using open circuit test data, this voltage represents the no load voltage V0, and this current represents the no load current I0, and this represents the wattmeter reading W0, which can be taken as equal to the iron loss of the transformer. And it is known that R0 is equal to voltmeter reading by IC, and which is equal to V0 by IC is no load current I0 into cos phi 0, and X0 is equal to voltmeter reading by I mu, that is equal to V0 by I mu is I0 sin phi 0. So to find R0 we need to know V0, I0 and cos phi 0. V0 and I0 are the given data, so we need to find phi 0, and phi 0 is found by W0 is equal to V0 I0 cos phi 0. W0 is the wattmeter reading and V0 is the voltmeter reading, I0 is the ammeter reading from the open circuit test data. So we can get phi 0, and by using this we can find R0 and similarly X0, which are the shunt branch elements of the electrical equivalent circuit of transformer. And now coming to the short circuit test data, which is performed on HV side, but HV side is here the secondary side. So by using this data we are getting the series branch elements R02 and X02, but we need to find R01 and X01. So first let's find the R02 and X02 by using this data. So this is VSC and this is ISC and this is WSC, and which can be taken as equal to the copper loss of the transformer. So from the given data, WSC is equal to ISC square into R02. So by using this we can find R02, and Z02 is the ratio of voltmeter reading VSC and ammeter reading ISC. So now after finding Z02 and R02, we can find X02, which is equal to the root over Z02 square minus R02 square. So after obtaining R02 and X02, then we need to find R01 and X01. And now R01 can be found out by R02 by K square, and similarly X01 is equal to X02 by K square. This is how we must find the electrical equivalent circuit parameters by using the test data.